All right, welcome back, everyone. My name is Artur Garcez, and I'm here with Adam White. This tutorial on neurosymbolic computing, or Nesy, and explainable AI, which became known as XAI, and which became very popular recently. So, as usual, please feel free to post your questions in the chat. I will speak for some 10-15 minutes, and then Adam will take over and go through the clear system and method of knowledge extraction and XAI. So my part of the talk is to try and convince everybody that we need knowledge extraction. And I don't need to tell you about all the success of deep networks, and you must have seen the picture at the bottom with the school bus. And if you haven't seen this one, you've seen the panda and some other similar pictures where, despite a lot of success and very relevant applications, deep neural networks can be fooled. They have issues of robustness, problems with energy consumption, too much of that, leading up to problems with fairness and ultimately trust. And a lot of interest has been then devoted to try and provide explanations for these systems, and a lot of promise associated with addressing such issues of fairness and trust through explainability. And maybe too much was expected of XAI, but let's see where we are now in this exciting area. So DARPA launched an explainable AI program, which at the time had this picture, and of course a lot more has been produced. There's been a recent special issue of a journal devoted to the programs and the projects there, which are a lot more advanced now. But at the time, this picture caught a lot of attention in that the idea was that, well, machine learning systems, deep networks, can just tell you that this is a cat, and then they were looking for explanations. So I think it was the DARPA program that coined the XAI acronym. Explanations, as shown here on the right, as identifying the features of a cat. And so this is a cat because it has fur, whiskers, and so on. And I would regard that as what people later called interpretable machine learning, as opposed to explainable AI. And I would argue that explanation through explanation require knowledge extraction. And I'll tell you a bit more about that. So if we extract knowledge, as in symbolic knowledge, from a deep network, and this may be in the form of logical rules, or it can be in the form of an equation, as Adam will exemplify later. Then we can prove soundness of this process. We can use something called goal-directed reasoning on the extracted knowledge, which gives us a proof history, which in symbolic AI is very relevant, because it doesn't give you just an answer, but the actual proof actually includes the explanation as to how that answer was obtained. It allows for modularity, modeling different levels of abstraction, and of course transfer learning and knowledge consolidation. We saw quite a lot of interest in knowledge consolidation in the continual learning session earlier. So you can reuse that knowledge, and it also helps with system maintenance, and if you want to improve performance of the system. So these are all the promises of knowledge extraction. This idea that has been an integral part of neural symbolic computing. So when we look here at the neural symbolic cycle, the idea is that you have some background knowledge which is symbolic, and that gets translated into a neural network which gets trained with data. And this trained network is explained through knowledge extraction. So these green arrows are essentially algorithms that allow us to bridge this gap between symbolic and sub-symbolic representations. We extract some knowledge, which can then be consolidated with the background knowledge, and then hopefully the process repeated. So this step of extracting symbolic representations from trained neural networks is what we call knowledge extraction. And it allows us to try and measure the knowledge that has been extracted with respect to the performance of the network. So this step is then measured through the concept of fidelity. So this is the accuracy of the symbolic representation with respect not to the data, but to the trained model, the neural network. So this is what early on was referred to as fidelity. And through this step of knowledge extraction, we would then measure fidelity. And this is very important, and the main point that I want to get across here, that this measure of fidelity is absolutely necessary and should precede user studies. Because for every complex problem, there is an answer that is clear, simple, and wrong. So we do need a measure of fidelity as we try to explain such models. And over the years, there have been many techniques looking at aspects of soundness, so making sure that the translation is correct. These have been broadly split into pedagogical, decompositional, or eclectic techniques. So where you look at the network as a black box, or you decompose the network and look at the inside of the box to identify what each part is doing. Early methods include the M of N method from the late 90s and the SILP method. And they have been frequently looking at extracting, for instance, decision trees from such networks, like the Trepan method, more recently the ERIC method. And they have also been applied to recurrent networks, and there, instead of extracting trees or graphs, you hope to extract automata. And the current work has been focused a lot more on layer-wise extraction as these networks became more and more complex. So focusing on a specific layer of the network. So in a kind of decompositional approach. Using soft decision trees and probabilistic versions of the M of N approach, distillation, and network querying, which is related to the logic tensor network framework, where you are allowed to query the network and probe specific subnetworks or neurons to see if you can derive some explanations for what's happening at that point. A lot of interest has moved on to applications as deep networks became also very relevant in practice. And in my own perspective and experience, we applied ideas of knowledge extraction in the gambling industry to reduce harm from gambling. So you have a system that is trying to predict whether someone may be at harm. And there, it's interesting because you have all these different dimensions of an explanation, and this is a new component. So before, in the context of neural symbolic systems, it was all about the translation algorithm, showing some fidelity results, and deriving a symbolic representation from the trained neural network. But now it's clear that there are different aspects of explainability. In this case, are we trying to explain the system to the regulator, to the operator, the gambling operator, to the player, or even to the data scientist who hopes to improve the performance of the system. So these different facets are all very relevant, and they're the representation, the type of symbolic representation and the level of abstraction may need to vary depending on the level of expertise. And then there's a lot of recent interesting work on drilling down into representations that are extracted from such systems. And in that area, we used the extraction of decision trees and something called risk curves, which have helped debug the system and improve the predictions. Now, the computational complexity in that neural symbolic cycle, the bottleneck is precisely in the extraction part. So computationally, the most difficult task is the extraction. So global knowledge extraction is a hard problem computationally. So that is why in practice, we may not be able to close this cycle and apply it many times, especially now that such networks have millions, if not billions of parameters. So instead of global methods, which seek to explain the entire model and derive such symbolic representations for the entire model, in local XAI, we seek to explain each case. And this is where you have the popular methods LIME and SHAP. And these have an important role to play in practice. But these local methods also require a measure of fidelity and an equation, a description to explain their alternative outcomes. So clear counterfactual local explanations via regression, which I'll pass on to Adam to detail, looks at that. Achieving such a measurable local explanation, so having a measure of fidelity for local methods, so that differently from LIME and SHAP, we can guarantee certain behavior and level of performance. Having this equation, which allows for counterfactual reasoning, and Adam will tell you more about that. And it's also contrastive when it's applied to images. These are the papers that are related to CLEAR as a local XAI method. So what I'll do next is I'll just go through some of the slides for some of the other stuff in terms of knowledge extraction from recurrent networks, because at the bottom there are some references, and then if you're interested, I can talk a bit more about those later. So in the case of recurrent networks, extraction of knowledge from restricted Boltzmann machines and deep belief networks, layer-wise extraction and probabilistic M of N approaches. There you have the references to Eric that I mentioned earlier. And in the case of querying the network, the logic tensor networks approach, where with Ben Wagner, we applied LTN to the problem of fairness, where you query the network and seek to improve performance there. If you're interested more in the LTN framework, then I would refer you to this paper here at the bottom. And before I pass on to Adam to focus on CLEAR as a practical, local, measurable method of knowledge extraction, just to mention that from my perspective, the key challenges are the extraction of meaningful concepts and relations between such concepts in the case of large networks. And then you hope to be able to reuse such concepts and relations in out-of-distribution transfer problems. And you also hope to extract first-order logic from such networks because of the expressiveness of these representations, allowing you to describe different levels of abstraction, for instance, in the case of normative rules. So I'll stop here. We can come back to some of the references and some of the approaches for global knowledge extraction, but I'll hand over to Adam at this point to tell us more about CLEAR as an exciting local method for knowledge extraction.
Right, okay, thank you, Artur. Before I start, I should just say I have a bit of a cough at the moment, so forgive me if occasionally I have to take a pause during this presentation. Okay, so as Artur was saying, I'm going to talk about the explainable AI method called CLEAR that explains single predictions of AI systems. Let me just clear this out. Okay, and as Artur noted, there are kind of two main approaches to explainable AI. The first is to create inherently interpretable and transparent AI systems. The second is to treat AI systems as black boxes and to then explain their input-output behavior. And such black box approaches can be divided into two broad types. Those which seek to provide global explanations of the entire system's behavior, and those that provide local explanations of single predictions. And you go for local explanations in part when the AI system's decision boundary is too complex to allow for global explanations. And CLEAR, as Artur said, provides local explanations. Okay, now CLEAR builds on the strength of two highly used explanation methods, but it also addresses their weaknesses. The first method provides a set of counterfactual instances, where a counterfactual instance specify close possible worlds in which an individual receives the outcome they desired. So, for example, Mr. Jones would have received his loan if, contrary to the facts, his annual salary had been 35,000 instead of the 32,000 he currently earns. Now, there are over 60 published methods generating optimal counterfactual instances, where optimality is kind of defined in terms of such criteria as actionability, sparsity, and plausibility. Now, we kind of are not great fans of using just counterfactual instances by themselves because they provide very shallow explanations. So if we stay with the Mr. Jones example, suppose Mr. Jones was assigned a probability of 0.75 for defaulting on a loan. A counterfactual, just providing a set of counterfactual instances by themselves would not explain why Mr. Jones was assigned that particular score. It wouldn't explain what the contribution of each of his features made to that score, and wouldn't explain things like how the features interacted to generate the score. For example, the AI system might in effect be multiplying Mr. Jones' salary by the number of years in which he'd been in his job. But you wouldn't know that just by getting a set of counterfactual instances. And I mean, can you imagine any other science which would treat statements of counterfactual instances by themselves as providing an explanation rather than seeking to discover the underlying governing law or a least equation? So it's surprising that people are taking counterfactual instances by themselves as sufficient for providing explanations. The other widely used technique is LIME, which we're going to kind of look at. At the end of the presentation, I'll briefly talk about SHAP as well. LIME stands for Local Interpretable Model Agnostic Explanations. Now, very briefly, LIME algorithm explains a prediction by first generating a synthetic data set of observations. Each observation is then passed through the AI system, which labels it with a forecast, and the labeled observations are then weighted on their Euclidean distance to the observation. So if we look at this diagram here, the orange patch will correspond to the space for which a classifier assigns the observation as, say, class 1. The blue areas correspond to where the classifier would assign the observation as class 0. The red cross is the observation to be explained, and the other crosses and circles are synthetic data points whose sizes are relative to how close we are to the observation to be explained. Having generated its synthetic data, LIME then carries out a simple linear regression and its regression coefficients are meant to explain the prediction. So here's an example of Lime's output. This is for explaining a prediction made by a random forest using the iris dataset. So on the right-hand side, you've got the values of the feature for the observation whose prediction is going to be explained. On the left-hand side, you can see that the random forest is assigning a probability of 1 to this observation corresponding to setosa. And in the middle, you've got Lime's regression coefficients. Now, although Lime displays regression coefficients, it does not show the corresponding prediction made by its regression. And we analyzed these hidden predictions and found they often had very large errors. For example, here are Lime's regression scores for this observation. And what you can see is that the score it gives for setosa, 0.54, is very different to the random forest prediction. In fact, you could say that the regression coefficients that Lime has generated provide no explanatory value at all in this case. And this highlights a key problem with Lime and with many other explainable AI systems, in that they don't report on their fidelity. So consequently, you don't know how reliable they are. And just to kind of summarize what fidelity is in this particular context, it will be on how closely the explanation method, in this case Lime, mimics the input-output behavior of the AI system it is meant to be explaining. And very often we found that Lime's explanations have very poor fidelity. Okay, so having kind of identified shortcomings both with counterfactual instances and with Lime, we then thought about what are the key requirements for a satisfactory explanation. And in doing this, we turned to the work of a philosopher of science, James Woodward, who in his seminal book, Making Things Happen, stated that an outcome is explained by specifying the causal structure that generates it. So when thinking about explainable AI, the causes are the input features to the system, and the effect is the classifier's prediction. Okay, and for Woodward, to specify the causal structure requires stating, firstly, a causal equation that relates the outcome, the prediction, to its causes, features. And it also requires stating a set of counterfactual instances that illustrate the causal structure by answering a set of what if things had been different questions. And the causal equation supports the counterfactual instances. And so that's Woodward's requirements, and we added to that the requirement that an XAI system must measure its fidelity. It must know when it does not know. Okay, having kind of decided on the requirements for explainable AI system, we then came up with CLEAR. And CLEAR provides local explanations which have counterfactual instances and their supporting causal equation. It uses the values of the counterfactual instances to significantly improve the fidelity of its causal equation. And importantly, it reports its fidelity, so you know when you can trust it. Okay, now before I go into the CLEAR method in detail, I first of all just need to define what we mean by a B perturbation, where B stands for boundary. Okay, a B perturbation is the minimum change needed to a feature in order to change the AI system's prediction to a desired class, where all other features are being kept constant. So an example of Mr. Jones, who would have received his loan if his salary had been 35,000 instead of 32,000. The difference between these two is 3,000, so that's the B perturbation. Okay, the minimum amount the feature had to change to flip the classification. Okay, so the clear method begins by sampling from the AI system, that's to be explained, to determine an observation's actual B perturbations. Next, clear generates synthetic observations and extracts from these a balanced neighborhood dataset. So whereas Lime uses all of the dataset and weights it on Euclidean distance, Clear just selects those points that are relevant to determining its B counterfactuals and its counterfactuals. And this covers the neighborhood from the observation to be explained to points just inside the decision boundary. Okay, a stepwise regression is then performed just on this neighborhood. Okay, then Clear measures the fidelity of its regression coefficients, and it does this by using the regression equation that it's generated to estimate the observation's B perturbations. Now, I don't have time to go through this calculation, but the general idea is that given the values of the features in the observation, the regression equation can be used to determine how much any particular feature needs to change in order to move the prediction to the decision boundary. The fidelity of the regression coefficients is then calculated by comparing the estimated B perturbation coming from the regression equation with the actual B perturbation values which were determined in step 1. So in this example, the difference between the two is 0.045, so that's the fidelity error. The final step in Clear is then to iterate to the best explanation. And this is possible because Clear reports on its fidelity. So the user can start changing parameters to see how much they affect the trade-off between interpretability and fidelity. So for example, if you increase the number of terms in the regression equation, then that might, if you increase the number, then that might increase the fidelity, but that might at the same time decrease the interpretability. But the key point is, by knowing how faithful your explanation is, you can then start playing around with the parameters to kind of come up with the best trade-off for you. Okay, here's an example of parts of Clear's output. This is for an observation from the UCI credit card or adult data set. And what it's saying here is that this particular observation had a probability of 0.68 of defaulting on the loan. And what you have here is you have the regression equation, and here you have some information on the counterfactuals and on fidelity. So if you look at the regression equation, you can see that Clear allows for quadratic terms, and it also allows for interaction terms. It also gives you a choice between multiple regression and logistic regression. And you've got a large list of parameters, so if you wanted, you could have a regression with, say, fewer terms, for instance, or without interaction terms. Now, if we look here, excuse me, you can see that for, say, feature pay 0, the input value, this is standardized data, is 1.8, and Clear, and the actual value pay 0 needed to have to switch the classification class was it needed to be reduced from 1.8 to 0.2. So that's so we're actually putting in the values into the AI system, the input data, we're able to find the exact value necessary to flip the classification. The regression equation here estimated that the 1.8 needed to be changed to 0.4. So in that case, we've got a fidelity error of approximately 0.2. Okay. Now we compared Clear with Lime over 5 data sets and over hundreds of observations, and we found on average that Clear's fidelity was 40% better than Lime. So if we look here, the blue column corresponds to using clear in its best configuration. The green column is Lime. You can see the sharp difference between clear and Lime in each of the data sets. This graph also shows some of the options you have for how you can run clear. Okay, now we've next developed a version of clear specifically for explaining the classification of images. And in order to explain that, it's easiest to first explain how Lime works, and then we'll explain how clear image, as we called it, improves on that. So, and we're going to use an image of a cat and a mouse to begin with, because that makes it very easy to explain what's going on. And then later on, we'll switch to chest X-rays. Okay, so in this example, Lime is going to explain why the Inception neural network classifies this image as being an American black bear. So it's being misclassified. And Lime's going to look at what parts of the image led to this classification. And the first thing it does is it uses an external segmentation algorithm, such as quick shift, to segment the image. In this case, it segments it into 55 segments. Okay, then having done that, it then starts, sorry, it starts substituting some of the segments and filling them in with just kind of gray patches in order to generate lots and lots of perturbed images, as you see here. So each perturbed image is a different set of segments being infilled with gray. Okay, and each of these perturbed images is then passed through, in this case, Inception, and we get the classification probability for it being a black bear. Just let me see so I can move that away a bit more. Okay. Now, having created these images and got the probabilities, we can then, in effect, have a synthetic data set. So each row corresponds to a separate image. And if a segment has been infilled with gray, then it gets a value of 0. If it's left with its original content, it's a 1. So we end up with this kind of binary data, and this final column is added of the probability of classification probabilities. This is then used to generate a regression model, and then Lime presents results where it highlights both segments with the greatest regression coefficients, positive regression coefficients in green, and whichever segments have the largest negative values are in red. So you can see here that large portions of the cat are responsible for the image being classified as being of a Great American Bear, whereas the mouse had a negative impact on that classification. Okay, so that's very quickly how methods like Lime and also kind of SHaP work. But kind of a key criticism is, well, is in its use of kind of gray segments to generate the perturbed images, because the perturbed images might then often be outside the classifier's training distribution. And using these perturbed images would seem to provide a very poor basis for evaluating segment importance. Now we'll come on to clear image. Now, clear image, by contrast, uses a GAN to generate a relevant contrast image, and then explicitly explains an image's classification relative to that contrast GAN. For example, we carried out an analysis of X-rays of patients with pleural effusion, which is a disease of the lungs. And the contrast image, so we start off here with the X-ray of a deceased patient that gets passed into a GAN, which generates a cured version of the X-ray. And both of these are then passed into clear image. And what we do then is we use the difference between the deceased image and the cured image as part of our segmentation algorithm. We also use the deceased image to generate our set of perturbed images. So rather than substituting segments with just grey patches like Lime does, we start off with a diseased image and we start replacing segments with the corresponding segments from the cured image. So if the image stays within the training distribution and it's relevant to the problem, what we're trying to do is we're trying to provide a contrastive explanation which explains why a particular image was classified as diseased rather than cured. Okay, and by having the nearest healthy image, we're providing meaningful contrastive explanations. That's our aim. Okay, so here's an example of a clear image output. So here's the original diseased image, and then what clear image has done, having done its segmentation, it's identified that the green, the orange, and the red are the segments which most contributed to this X-ray being classified as having a probability of 1 of having an fusion. Here's the regression equation. In this case, it's a logistic regression. And what we're able to do with clear image is, which other methods, no other explainable AI method has done previously, as far as we're aware, is we're also able to identify cases of what's called causal overdetermination. So causal overdetermination occurs when two or more sufficient causes of an event simultaneously occur. So a standard example from philosophy is a set of soldiers in a firing squad all simultaneously shooting a prisoner, and each shot is sufficient in itself to kill the prisoner. We'd then say that the death of the prisoner was causally overdetermined. Now, this kind of causal structure may well be ubiquitous for learning systems. So in our example, Clear Image was able to identify 3 sufficient causes, when those were segment 3, 5, and 8. And each of these by itself was sufficient to cause the X-ray to be classified as having very close to a probability of 1 of having pleural effusion. And this means that if you were to, say, substitute segments 3 and 5 with their corresponding healthy segments, it would make practically no difference to the classification probability. In order to cure this image, you have to substitute all 3. Okay, now here are some of the results we got for Clear Image. If you look at the left-hand column, these were the original X-rays for patients with pleural effusion. But luckily in our team, we had an A&E specialist who annotated each of the X-rays and put a red patch over the areas which he felt were responsible for each of these X-rays having been classified as corresponding to pleural effusion. And these red patches, the outline of them is included in all the other images in blue. And what we're doing here is we're comparing 4 explainable AI methods: GradCam, which is the benchmark for explaining image classification; Lime, Extremal, which is a Facebook method; and Clear Image. And what you can see is that GradCam, and then for each of the explainable AI methods, the darker the red, the more importance that XAI method is attributing to that particular part of the X-ray. So if we took, say, Lime here, this part, it's saying the segment of greatest importance is this small bit here. Now, if we look at GradCam, which is constantly being cited in papers on COVID and AI and so on, we see it performs very badly. It's very kind of fat-fingered, if you like, covering a large part of the X-ray. And it performs very poorly on the 2 measures we used for evaluating each method, which was a pointing gain and also intersection of union. GradCam It's not the worst, but it's still very poor. Here we have line, which is often completely missing segments. Similarly, Facebook's method, and here we have clear. Clear performs the best. Its segments are kind of often the kind of most precise, and it has good overlap on the whole. It's far from perfect though, but it does, if you look here on the matrix, it significantly outperforms the other methods. And the reasons for this primarily are down to the benefits of using a GAN for a contrast image. It allows us to make a much better segmentation because we use the difference between the original X-ray and the cured to help guide what the relevant segments are. And then when we're doing the infilling to create the perturbed images, we're staying in the training distribution, and our perturbed images are meaningful, not full of gray patches or other techniques use like blurred patches or whatever. So the GAN is kind of critical to the success we're getting with clear image. Okay, a few other points. Another kind of key explainable AI method is SHaP. I'm just going to very briefly go through that insofar as it's there are different versions of SHaP, but the one which is most commonly used is kernel SHaP. And kernel SHaP is very, very similar to Lime. Like Lime, it generates synthetic data, does a simple linear regression, but it differs from Lime primarily in its kind of when it comes to doing regression and in how it weights the data points, and it weights them in such a way as to produce what are called Shapley values. And Shapley values come from game theory and identify the marginal contribution each feature makes to a prediction. Okay, but like Lime, SHaP doesn't measure its fidelity. And we found when we started looking at the regressions, they often have very poor R-squareds. Another key problem with this, it answers the wrong question. What it does is it explains a prediction relative to a base value. Now, base value is the average forecast taking of all the data in the training data set. So it looks at all the forecasts, takes the average, and then explains why this particular observation differs from that average of all the data in the training data set. It's unlikely the user really wanted the answer to that particular question. That's not the contrast they were after. They might be after a contrast between a healthy X-ray or just an absolute probability, not this contrast to this kind of often irrelevant baseline. So SHaP is incredibly popular now with banks and consultancies and so on. But it's the assumption of linearity. It also summarizes data. So if you start off with particularly the iris data set in its entirety, it takes that and it summarizes it down into just 14 rows of data before it does its regression. So a lot of information gets lost in SHaP. But because it's based, perhaps because it's based on this very clever idea of Shapley values, it is very popular. But no measure of fidelity. I just want to emphasize that. And so you're left with this question of why should you trust it? Okay, and when we looked at, when we run SHaP and compare it with Clear, so this is the example earlier from the UCI credit card data set, we see significant differences in some of the feature weightings. And this is on, and I picked this observation, this is one in which Clear did, its fidelity was good. Yeah, so by inference, SHaP's performing poorly here. But you wouldn't know that if you just look at SHaP's output, because it doesn't ever report its fidelity. Okay, a few other things to say. Clear is available on Github, and we've included instructions on how to download it. It is a research prototype, so it's not a kind of robust commercial product, but people have successfully used it. And if you want to, please have a go. And if you have any problems, I'm very happy to receive emails and kind of give advice on how to interpret it and so forth. And finally, next steps we're going to do with CLR is we're just kind of kicking off a project looking at kind of fairness AI, and particularly interested in some of the global fairness algorithms, and we're going to use CLR to kind of look at the details of how these algorithms are adjusting predictions. We also want to add some semantic segmentation to CLR image. So at the moment, the explanations we go back are of this form where it says segment 3, segment 5, segment 8. What we really want to do is to translate those into descriptions of actual parts of the lungs. That would be a big boost to improving the explainability of CLR image. And the other thing we need to do is user trials. So as Artur said, first, most important thing, but before you get into user trials, you have to do fidelity. And most explainable AI systems don't do that. We just go straight into the user trials. And given users don't know what the AI system's internal logic is, I'm not sure it's that meaningful in itself for users to say, yes, that's correct. Okay, thank you for listening to me. We're very happy now to take your questions.
Great. Thank you very much, Adam. So I was monitoring the chat here, and there are two general questions I think I can answer. One was about explainability and interpretability and the use of the terms, and which one is more accurate. And I think it's I don't think there are proper definitions. So it's difficult to answer, but from my perspective, interpretability has a lot more to do with individual explanations, perhaps. And when I look at explaining an AI system, to me, the important ingredients are either a proof history that would allow you to provide the explanation as to how the result was obtained, or an equation, as in the case of CLR, which allows you to ask those counterfactual questions. And so interpretable machine learning has been used more broadly. To me, explainability requires either a proof or an equation. And just to add to the confusion, there is also comprehensibility. So whether the system is comprehensible to a user is an extra dimension also there. Another question was about the knowledge extraction part, whether it was using the training data or not. So typically, we use the data to train a model, and then we apply an algorithm to extract knowledge from the model. So it's not directly using the data, but it's indirectly, of course, was trained with some data. So there are systems of explainability that actually require access to at least some of the data. But in general, it shouldn't be like that. You should have access to the system, not necessarily knowing which data was used for training. Then, of course, having access to either querying the system to generate data from it, or inspecting it if you can dissect it or decompose the system. So that was that, and maybe if there are other questions specifically about CLR, maybe let me see here. How does CLR consider the human user that wants an explanation? So maybe that's one for you, Adam.
Okay, well, if I was to show you the full output from CLR, it includes kind of bar charts, regression, and so on. And you also have the option to simplify, well, to specify how many terms are included in an explanation and to simplify the equations slightly. So the idea would be that, first of all, get a faithful explanation, one with a fidelity level that you're comfortable with, and then you can think about how to represent the explanation for different audiences. So a data scientist might want a great deal of detail, but when it comes to the user, you might just want to provide them with, say, a bar chart, just highlighting which features are most important, and also a handful of counterfactuals. So it will vary. But the key thing is, first of all, provide a full explanation, at the level of fidelity you require, and then think about simplifying from there to a particular user.
Thank you. Anyone else would like to raise your virtual hand? If you want to ask a question, we can ask. If you would like to be unmuted, if you don't want to post it on the chat. Anyone?
Does anyone have any experience with using some of the other systems? That would be interesting to hear. Other explainable AI systems, that would be interesting.
Exactly. Yeah. So we have here, I'm not going to pronounce your name properly. Sylvia.
It's Sylvia, yes.
Sylvia.
Thank you.
Please.
I was just wondering if, in general, any explainable AI technique has ever been used for adversarial examples? And if yes, then what was the result? What have you seen anything interesting?
I've seen in the context of adversarial examples and adversarial attacks and robustness in general. There's a whole community, a whole new community on verification of neural networks. And so they organized the AAAI Spring Symposium last year. One of the co-organizers was Alessio Lamuscia from Imperial College London. And in that community, they have been looking at providing guarantees or proofs of robustness. But I haven't seen a direct connection between those results and work in explainable AI more generally. But I think you're right that it's important to, again, if you derive explanations, so descriptions of what this system is doing, it makes a lot of sense to look into those from the perspective of, is it robust? How is it addressing those spurious examples?
So the only literature I have seen has been about avoiding identifying adversarial perturbations. So you try to make sure the segments are large enough, kind of have some regularity in shape, and it's all about avoiding giving non-robust explanations and trying to avoid just highlighting these kind of peculiar features and trying to kind of capture the typical behavior of the AI system.
Okay, thank you very much.
Thank you, thanks. Yeah, it's a very exciting area as well to look into and seek to relate with explainability, yeah.
Yeah, I mean, likewise with, say, counterfactual instances. Counterfactual instances don't want to find those peculiar points where the behavior of classifier drastically changes. So work goes on trying to avoid that, but it's all about avoidance.
Yeah, I can think of generating data, selecting data, again, to avoid or to evaluate. But I think also that in the context of if there are proofs of certain behavior, then perhaps there's a bit more that we can do there if we can provide bounds on network behavior. But yeah, exciting stuff. Anyone else? Anyone as brave as Sylvia who would like to raise your hand and ask a question? This is supposed to be a tutorial. So we could be, Adam presented a slide at the end with the GitHub, just to emphasize, please do visit and try some of the examples there. It would be great to have more people trying the system, trying to break it, trying to apply it to new areas, and starting from some of these simple examples like the iris data set and some of the other examples that are available there. I think it's probably the best way to go in order to know exactly the details of it. I think what is difficult sometimes right now is that some of the systems, they are made available, they provide an outcome, they give you a result, and you tend to trust that result. When in fact what we need is to be able to ask those what if questions and to have some guarantees as to how good those results are. So knowing when you don't know is key here, I think, and it's the fidelity measure that gives you that ability to be able to interact in a kind of skeptical way with the system, and then fine tune it to your needs. Okay, if there are no more questions, I think we can stop here. Thank you all. Thank you, Adam. Anything else you would like to add?
No, happy.
Right, so now we have a break, and then we come back for an exciting keynote by Josh Tenenbaum. Yeah. Thanks, everyone.
Thank you.
Thank you. Bye.